picture will be in front of the Numekis building. We will reach you after the talk. So the second lecture of Patricia.
Thank you. So I'm going to recall a bit where we left yesterday. So for today, our position, it will be a circular maze. So instead of the line, I'm going for a circular maze because you remember grid cells are periodic. So if I'm on a circle, it will be easier. Okay, and if I recall what we said, if you have a position S, in fact, the brain does not see that. It will have, say, a receptor field here for N1, and N1 is going to spike. So when it starts, there is something before, and then it starts to spike more, and you stop it at T, okay? And now our problem is a bit different because we are going to have, okay. Let me see, I think I will need a lot of color. So you have, in fact, two positions, say S1 and S2, okay? And now you have several cells. So you can have cells that are firing for both of them. So say this is N2. You can have cells that are firing only for this one. This will be N3. You can have cells that are firing only here, and so they will not fire if you are at S1 or S2, okay? And now what I want to know is, okay, I'm going to have, so if you look at the time, what will be going on is that N2 will also spike a lot if I am at S1, okay? N3 is going to spike a lot. And N4 is going to be pretty silent, okay? That's my N4. And so now I want to be able to make a test of H0, if you want, S is equal to S1 versus H1. I think I will call them hypothesis 1 because it's S1 and hypothesis 2 because it's S2, like that, okay? So I want to be able, by just seeing that, to be able to know if I'm in S1 or S2. Okay, so I will need a little bit of notation. Yeah, okay. First, of course, you will have two errors. The first error is when you are in S1 and the test is saying S2. Okay, that's the first error. The second error is the probability when you are in S2 that the test says S1. And you are going to look at the maximum of that, and this will be the error of your test 5. Okay, so this is your test 5. Okay, and what we want to understand first is what is the order of magnitude of that for a given set of neurons where I know where the receptive fields are. So, saying that I know the receptor fields, it means that I'm going to say that my firing rate for neuron I is going to take, so this is neuron I firing rate. It's going to be mu if Ni is active for S, and it's going to be 1 if not. Okay, and you have the assumption that mu is, say, much bigger than 1. Okay, so this means, for instance, that here neuron 1 is, the value is mu, whereas here for neuron 1, the value is 1 for the firing rate. Okay? And if I want to understand what's going on, and if I know that, like the brain knows what are the receptor fields of each of the neurons, what is important is the number, so IS1F is going to be the set of I such that I is active at S. So here, for instance, it's 1, 2, and 3, whereas IS2 of S will be just 2, right? Okay, so that's my set of neurons. And you see that, in fact, neuron 2 is completely useless to understand if I'm at S1 or S2. Okay, because they fire the same if I am at S1 or S2, because I'm in this receptor field. So what is important, in fact, is the set IS1 of F minus IS2 of F, or maximum with this one, IS2 of F minus IS1 of F. This number, I called it delta S1, S2, and that's the maximal number of cells that can behave differently when I am in S1 or S2. Okay? So say, for instance, like here, that this is in fact the first guy, okay? Because here you have that IS1 of F minus IS2 of F, this is just 1, 3, whereas the other one is just empty. Okay, so we are going to concentrate just on this part. And so what we can do now is we are the brain, so the only thing that we have access to is the number of spikes of I until time t. And if you think about it, a good test statistic will be, let's call it Z, which will be the sum for all the I in IS1 F minus IS2 F of this NIT. So it means that I'm gluing together the spikes that are here with the spikes that are here. Because I know that those are the cells that are going to spike only if I'm at S1, and they are not going to spike at S2. So if the rate that I get for the sum is very big, I'm going to say, okay, S1 is the one that is firing. Yes? Okay. So this thing is what? It's a Poisson with parameter what? This is my delta, S1, S2. And then I have T times mu if S is equal to S1. And this is just a Poisson with parameter delta S1, S2, T if S is at S2. Okay? So I'm going to say, okay, so my test is going to say Z, if Z is bigger than some threshold, then phi votes for S1. Okay. Now there is a small result, but it's easy to prove, is that if you have, if P is a Poisson variable with parameter theta, then the probability that P is bigger than theta times 1 plus x is always smaller than exponential minus theta x squared divided by 2 times 1 plus x3. I don't care about the constant, but it's just to use the order of magnitude. So it means, for instance, if I'm going to use that, and if I say that the trade between this guy and this guy, okay? So it showed like delta t mu 1 over 2. See that I can rewrite this as delta mu divided by mu. Here I have the parameter theta. Here it's my 1 plus. So it means that the probability that Z is going to be bigger, sorry, forget about that. I want to understand what is the error. So I want to understand under S2 what is the probability that P is going to be bigger than its threshold, which is delta T mu plus 1 over 2. Okay? And the theta is here because I'm under S2. Okay, so it's going to be smaller than exponential minus delta T, and then you have a constant that is going to depend on mu because of that. Okay, so that's your order of magnitude for this special test for the error. Okay? And you see also that if you want to make this smaller than alpha, say 0.05%, it will be implied by saying that your delta t is going to be smaller than a certain constant, which means basically that the time that you need to observe your system is going to be of the order c over delta. Okay? So say differently, if I want to be sure with only 5% of mistakes that I am in S1 and not at S2, what I have to wait for this time to happen is a constant divided by the number of cells that are spiking differently when I'm at S1 with respect to S2. Yeah? It's clear? For the moment, it's not minimax. It will arrive. Okay. So here, that's what I was saying. That's the test that we built. And I just showed you the upper bound. In fact, you can show that it's the best thing that a test can do. Like of all the tests that you can possibly imagine, the best thing you can say is always of the order exponential minus t, another constant times delta. There is a small constant. This one is only when t is not big enough, but as long as t is big enough, this part you don't care. And so you see that my error that I put over there, it's really the good order. So for the best test ever that the brain could do, the rate, the time of observation that it needs is 1 over delta up to some constant. Yes? You tell me if it's too fast, okay?
Big enough, exponential minus t is very small.
Yeah, but this one becomes negative. So in the max, it's only that remains. So that's just there for the beginning. Okay. So just to show you that it's really 1 over delta. So we made some simulations in a lot of different cases for the grid cell, place cell, choice, etc., etc. You see that they all align on a line. So this is the 1 over delta here, and this is the time that you need by simulation to have less than 5% difference. And you see that, okay, the 1 over delta rate is really the one that you need. And it also means that if there is no cells that are spiking differently between S1 and S2, of course, then the time becomes infinite. Meaning because there is no cell that is able to discriminate between S1 and S2, it also means that it takes you an infinite time to discriminate them. Okay. So now I will represent it like this. So like this is a receptor field of my neuron, and well, I say it's interval, but it's interval on the circle. And the first thing you can prove is in fact that whatever the code, so I'm not speaking about grid cell, place cell, because a code can be very, very complicated, right? A code, if my only restriction is that it takes only 2 values, I can have codes that are as weird as that. It can be mu here, and then it's silence, and it's mu here on a very short spaces. It can be very big until here. Why not? This would also be a code. It's not a grid cell code. It's not a place cell code. It's something even more complicated. It has 2 values, right? What you can show is that if you have only n cells that are behaving like that, there is always at least 2 points, S1 and S2, that are at distance less than 2 to the power minus n, that your code cannot discriminate. Because somehow you are making a union of intervals, and you have only n of them, so it's like the number of parts you can make, and you have 2 to the power n parts, so there is at least 1 part which is going to be bigger than 2 to the power minus n, and you put the 2 pieces here, the 2 S1 and S2, and those you cannot discriminate. Okay, so that's the best thing you can do. And you remember the grid cells were having a Fisher information which was exponential, which has the kind of same flavor. Like the precision that the grid cell is going to have is going to be exponential, and being below exponential, it can be very tricky because of that. Okay, and here arrives the minimax rate. So now what we want to understand is, okay, so I know what is my minimal time. It's this 1 over delta. It depends on my code. And I know I don't want to look at particular S1 and S2 because I know that I can find some S1 and S2 that are far away that I cannot discriminate. So I want to be in the worst case scenario. So I'm going to look at all the couples that are at distance at least rho. Okay? So now on my system, I have S1 and S2, and the distance between them is at least rho. Okay? And now what I would like to understand is what is the best code? So what is the code F that is giving me the smallest worst case scenario distinction time between S1 and S2? Yeah.
How do you define the set?
I will arrive there. So for instance, F will be the place code, the place cell code, or the grid cell code. And I will define in each of them, it will be another problem to find, depending on the kind of code I'm looking at, what is the best code inside a given rigid set of constraints. Yeah, you will see, yeah, yeah. We could speak about models if you want. But in the sense that it's a model that the brain is putting and not a model that the statistician is making. Yeah, but yes. Yeah, exactly. Yeah. Okay, so of course, first, the best code that is achieving that, it might depend on rho. The way it's posed, this this best code is going to depend on the distance. So we are going to search also for adaptive codes, meaning that in a certain range of rho, the same code is going to give us like the best time you can think of. And the question is it possible to have a code that is able to give you the best distinction time, whatever rho, or in a certain range of rho? Okay, you will see example after that. Okay, so that's our two problems, finding for fixed rho what's going on, and if you have adaptive codes. Okay, that's what I said. Okay, so now the first family, which is place cell code. So a place cell code, we are going to say that in this family, you have your cycle here. You pick AI and BI on it, and you are seeing that here you have your value mu, and here you have your value 1. Okay? So that's a place cell code, meaning that it's only one interval. It's not like the other one. You are forced to have just one interval per cell, which is the receptor field of this cell. Okay?
The choice of mu is part of the code.
What?
The choice of mu.
No, mu is fixed. It's fixed. You can imagine it's 30 Hertz or whatever. It's fixed. For biological reasons, we know that the neurons cannot have very high firing rates. So it's in a range, and we don't. And for this problem, we said that all the cells have the same mu. So the only thing that changed from one cell to another is the position of the receptor field. And so what we proved with Guilherme is that this minimax discrimination time, maybe forget about this formula, which is a bit weird, it's the integer part of a constant times n rho. The integer part is important because it means that if rho is too small, smaller than 1 over n up to some constant, then the time is infinite. So I told you, like, if I don't put any constraints of the code, the minimal distance that I can discriminate is 2 to the power minus n. If I force the code to be just one interval for one cell, T is, sorry, this is okay. This, but for the family P, which is the place cell code. Okay? Okay, so first thing, you get out of that you have a minimal distance donc for place cell minimal detectable distance is rho of the order 1 over n. Okay? After that, when rho increase, the time is of the order of 1 over n rho. Okay, so if rho is big, you can hope to make your discrimination faster. N is the number of cells, and rho is the distance. Okay? So there is a row below which you cannot detect, and once you pass this, then you behave like 1 over n rho up to some constant. The problem said like that is that it's a lower bound, and it's possible that the code that achieves that depends on rho. So let's see how we can make that. Okay, first, why the 1 over n? The 1 over n is there because, of course, if this is 0, 1, you can always have one cell which is doing that with this, which is 1 over n. And then another cell which is doing that with this, which is 1 over n. And you continue like that, okay? And each time you have a new cell, okay? Understand what I mean? So each cells have a different disjoint receptor field, each of them with size 1 over n. So of course, if I take two guys at distance 1 over n, I'm just in one cell, I cannot discriminate. If I'm going to be bigger, like if here I'm taking S1 and here is S2, well, you see that IS1 of F is like the white cell, IS2 of F is the orange cell. So the difference between the two, it will be maybe 1 or 2, depending on how you count, but it's fixed. There is no way that because S1 and S2 are very far, there is more cells that are going to respond to them with this code. So this explains that we can really reach the 1 over n, but this code is stuck, whatever row. For this code, you have that this minimax rate is 1 over n. It cannot, well, the number of up to some constant. It cannot go faster than that. Okay, one other thing you can do is say, okay, here I'm putting row. So now I'm dividing by step of size row. And if I do that, of course, I don't have n cell. I can have here, so it's 1 over row, different receptor field. And so it means that now I can put n row cells that have exactly the same receptor fields. You see what I'm doing? Now since row is bigger, once I have partitioned my circle, I have 1 over row different zone, but I have n cells, so I can put several cells with the exact same receptor field. So I'm going to double them or triple them until the number of cells that are at exactly the same place is of the order n row. Okay, if I do that, then of course I can discriminate at distance row or 2 row. Okay, forget the factor in it. And the number of cells that are of a given difference is exactly n row, which means that the time is 1 over n row. So I can reach the 1 over n row with this code. But again, if I give you the row, I made the code for this row. Okay? Okay. Now we can do adaptiveness. How do we do that? is by doing that. So now you are still your code, and your first cell is going to be a half circle, like that. And then your second cell is going to be like that. And you continue all the way over, like that. Okay? So this part is 1 over n. Now if I'm taking here S1 and here S2, okay, they are distance 1 over n, the difference is just 1. But if I'm putting here S2, the difference, you see now you have 2 cells that are difference between S1 and S2. So in fact, the more far away I'm going on this code, the more cells are going to fire differently between S1 and S2. So this one is going to be adaptive. So that's what I'm saying here. So that's the 2 examples I gave you after that. And so this code, which is what we call G, it has really it's a G that doesn't need to no row to perform. And once it's put in this way, for all the row between 0 and 1/2, you will have a rate which is in 1 over n row, with again the integer part, because you cannot go beyond the 1 over n. Okay? So for place cells, you have adaptiveness, meaning you have one code which is able for several rows to give different rates. And in particular, it can accelerate. Like if row S1 and S2 are very close, the problem is difficult and it takes them a long time to make the difference. But if S1 and S2 are very far away, then the time is going to be smaller, because you can use the fact that they are far away to have more cells that are different between the two. Okay. Also, I will not prove it, but this is good for biology. If you pick AI and BI at random, meaning your receptor field is just put them at random. Here it was very precise, right? Here I'm just putting them at random, uniformly. AI and BI, I just uniform variables that I draw on the circle. Then you can prove it's adaptive as well, except that it doesn't go to 1 over n, it goes to 1 over root n. Root n, square root of n. So it's adaptive again, except that it cannot go to the distance 1 over n, it has to have a distance 1 over square root of n. But past that, it is adaptive in the same way that this very precise code was.
How many cells do you have?
In your brain, I don't know.
Because it is
Yeah. No.
number of possibilities you can distinguish.
They recorded in rats several hundreds, but they record it, so I don't know to which extent. And the problem with place cell or grid cell is that if you don't measure them, you don't know that it's not anatomically they are place cell. So I don't know. Maybe you have to ask a biologist.
Okay, second question. So, picture to that whole cell. Do it by TMS or how do you do it?
TMS.
How do you identify magnetic simulation?
So how do we identify place cell for?
Yes, because you must identify the region in which the cell.
Yeah, it's because you let the rat run in here your circular maze, and you are putting a dot each time it fires, and usually you will have very low fire here and a lot of thing here. What? In the rat, yes. Yeah. Yeah. Yeah, on humans, I don't know. Okay. And now we turn to grid cell. Okay, so place cell, it's okay?
May I ask that last
Yeah,
question?
yeah, of course.
So if you make it more and more complicated mazes, more possibilities, at certain point the heart is not, you will not be able to distinguish things because you have too many possibilities. Is that correct?
I don't know.
But probably. So
Probably.
Your theory suggests this.
Yeah. At least what is sure is that if it's too close, they shouldn't be able to make the difference. Which is also something that even us, we know that,
Yes, we know that.
we are not able to localize ourselves at 1 millimeter.
Or you cannot distinguish the varieties of white as light.
Yeah, exactly. So it's a kind of same idea, because with place cell you can encode more than position, in fact. So, okay, now grid cell code. Yeah.
So you have mu said, well, standard hertz, because it's, but if you want to distinguish between so many different, you must use different frequencies.
No.
I suppose that different cells, they all have the same frequency.
Let me show you. They don't have all the same frequency, but look at that. It's not like you have really much more spike for the red or the green or whatever, right? The rat was traveling there at the same speed, right? So the place and time, it's the same. So the frequency is almost the same, but what changed is, for instance, this one is short, this one is super big. So in this sense, it's really the receptor field that moves, the firing rate, maybe a bit, but not that much. Okay? Yeah. And same thing here, yeah, by the way. For the grid cell, you see there are different grid cells, and the density of spikes is somehow the same. It's just that where they are really different. Yeah. So grid cell. So, yeah. So here I want something that is periodic, right? So if I start like that, and for instance I'm 1/4 periodic, I want something which looks like that, right? That's going to be my my grid cell. So in fact it means that its firing rate of the cell I, so J is going to be my module, and it's associated with a period that we call lambda J, okay? So here, for instance, lambda J is 1/4, okay? And what we are going to say is that, in fact, what is important is the modulus of, is S modulus the period, because we want to go back to where the point here in this period here, and then we are going to apply a place cell code just here. Okay, so this thing is going to be mu on a certain interval AI, BI, J. But here I applying to S modulus lambda J and 1 on the complementary. Okay, so it means that, for instance, if I'm here, this is my S, here is my S modulus 1/4, and because here it's null, but it's null here. So that's how I propagate my function, which is a place cell on just 0, 1/4, to a place cell, a grid cell, which is periodic on the whole thing. Okay, just one thing. I told you the minimal discrimination time was 1/n rho. You remember? About with the integer part. In fact, this one, it's the period. So if I'm going to look at it inside, it's going to look like that. Okay? So on modulus J, because I'm stuck with something of size lambda J, this is the rate that I'm going to have inside the things that have a period lambda J. Okay, so this is just to keep in mind. Okay, what else? In a module, so we have period J and we have NJ cells inside the module. Okay, because we are going to have, like the module, module 1, it corresponds to period 1. And of course, this is the place cells, so we can use again everything we computed. But then when you go down, module J is going to have a period lambda J, which means by the way, that you need that 1 over lambda j is an integer, because if you don't have that, you are not going to make it periodic on the circle. And in fact, what we need, because we want that each module communicates with the other one, we will need that lambda I plus 1 minus 1 is an integer. Okay? So that if you go to modules, maybe I change colors. If I go to, say now I have modulus like that. So here, this is 1/6. So for instance, this one is my second scale and this one is my third scale. And I need to be able to put it like that so that inside my stuff of length 1/4, I have 3 guys. I think I messed up, it's 112. Inside, you see what I mean? So this modulus number 3, inside modulus 2, it has 3 replicates. And inside the big modulus, it's going to have, so 12, right, replicates. Okay? The picture is clear? Yeah? Okay. Okay, the formula is intricate, but don't be afraid, I will explain. And that's why grid cells are so complicated to study. So the lower bound. First, you see there is a minimum here. So in fact, we are going to take like the worst case scenario of all those sums. So let's look at what happens for k equal 1. Okay? When you are at k equal 1, maybe here. When you are at k equal 1, so modulo, no, what? K and j are the same, so it's modulus 1, k equal 1. What you get is n1 over lambda 1 times the infimum of rho and lambda 2. Okay? So imagine that your rho is smaller than lambda 2, because if it's bigger than lambda 2, in fact, you are just using modulus 1 to do something. Okay? Well, maybe let's do it like that. If rho is bigger than lambda 2, it means that the minimum value is n1 over lambda 1 rho. Okay? n1 over lambda 1 rho, I told you, well, it's 1 over that. So it's the rate just of the place cells. So you need the place cell system, because you have an integer part around it. You need the place cell system to be able to detect rho, because rho is bigger than lambda 2. Okay, if rho is smaller than lambda 2, then the maximum is lambda 2 here. So it means that your first term is n1 over lambda 1, lambda 2, integer part. And it means, therefore, that lambda 2 has to be detected by lambda 1, by modulus 1. If it's not detected, if it's too small to be detected by modulus 1, then you have a hole. Because you want to detect something which is smaller than lambda 2, but already lambda 2 you cannot detect, so you're screwed. Okay? And even if module 2 would help you to find rho, lambda 2 by itself will be stuck, because module 2 cannot distinguish points that are at distance lambda 2, because that's its period, right? So for him, 2 points at distance lambda 2, they are exactly the same. So if it's not module 1 that is taking charge of the period lambda 2, then nobody will detect lambda 2, and then you're screwed. Okay? So you need to have a coherence between all the modules, and this is what we said here. We need that each lambda k is detected by at least one of the i's that are smaller than k. The factor k that we have here, we don't know if it's really there or not. But if you don't have that, this is really this information that you need it to be detected by at least one of the modules that are larger than the scale you are at. Okay? Once you've passed that, if you look at the sum, you will have a sum for k equal, for I equal 1 to k. Here you will ni over lambda I, and then you have rho. okay? But it's a minimum over k. So in fact, what is important is the smallest, well, the k which is the smallest, which detects rho, and after that, the other one, you don't care for the rate. So it's as if in this grid cell system, everything, all the modules for which the period is larger than rho are important. The ones that are smaller than rho, you don't care. They will not be of any use to make you detect rho. And on top of that, you need the modulus to be coherent with themselves, so that module of size lambda k has to be detected by the one before. Okay. And you see here, it's the rate for a family where we said I fix ni and I fix lambda I. So I'm kind of, yeah. Yeah.
So the minimum is not for k equal 1.
Yeah, but sorry. I should have said it like that. So it's lambda I plus 1 for all the I such that lambda I plus 1 is bigger than rho. And then from there you have the k, the limit k for which it's exactly rho. And then, well, no, sorry. The limit I for which you have exactly that. And then you will continue, because the maximum will be this one, with nk over lambda k rho. So you see all those terms you don't care in the minimum. And so the only term that matters is the last one. Well, the first module that is able to detect rho, and after that, you don't care. Okay? Okay, for the upper bound, we kind of get, except that the integer part is not at the same place. But we get somehow the same thing. What we did is that to get that, the cells that we put on the module, we took them either as the adaptive codes that I told you with the half circle, but on a period lambda j. So the half circle has of length lambda j over 2 now. Or we can put them at random, as we did before, inside the module. And so we get almost the same rate, except that the integer parts are not exactly at the same place, so we don't have an exact match between upper bound and lower bound yet. But, well, okay, that's the best we could do. But this does not answer a very big problem, is that we can do this computation when we know ni and lambda I. And now if I'm looking for what is the best rate, if I don't precise what is ni and lambda I, the only thing that, oh yes, I forgot to say that, I have the same budget for cells. So it means that all my modules, they need to have at most n cells, right? Because if I don't have that, there is no comparison between place cell and grid cells. So if, for instance, even if I fix lambda j, for instance, lambda j could be 2 to the power minus j, even if I fix that and I just let the repartition as I want, I don't know how to solve the problem. Well, we don't know. We tried a lot. We don't know. But we proved a lot of interesting stuff. We proved, for instance, that there is a code which reaches the 2 to the power minus n. So let me explain you that. So the extreme dyadic code is like this. So you are really doing lambda j equal 2 to the power minus j, maybe plus 1, I never know, something like that. But well, it scales, it's 1 over 2, etc. And you just take one cell, so nj equal 1, which means that your number of modules is equal to your number of cells. You have just one cell per module. So what does it do? I will represent it on the line because you will see why it works. It's better than... So on a line, it means that, okay, this is your 0, 1. And then this is your module 1, okay? One cell, half a circle. Module 2, it's going to be this thing, okay? Module 3, it's going to be this thing, like that, okay? And if you think about it, what I'm looking at is my first digit 0 or 1, my second digit 0 or 1, my third digit 0 or 1. So in fact, with that, I'm able to write on n cells all the digits up to 2 to the power minus n. And so that's why this one is able to reach this precision, right? So that's what I said. This one is able to reach rho to the power 2 to the power minus n. But if I take a S1 that is here and a very far S2 which is here, that have exactly the same digits after that. If they have exactly the same digits, it's only these cells that is making a difference between S1 and S2. So my delta is just 1. So this code, it cannot go faster with the distance. It can reach the precision 2 to the power minus n, but the time of discrimination is fixed at 1. It cannot go faster, even if the S1 and S2 are very far away. Okay. There was one last thing. I will not go too much into details on how to get that. It's again with lambda I, which has, so it was -1 and not +1, okay? And then we put exactly the same number of cells per module. So we don't go as deep as 2 to the power minus n, but we have more cells per module. And you can prove that you can reach the rate log 1 over rho divided by n. So in this sense, for fixed rho, if you make the grid cell know what is the rho you want, you can have a faster detection time with grid cells and place cell. But you have to know in advance what is the rho you want. Because once you have reached this rho, because of the same thing as the DID called, you're stuck. Okay. So I arrive at the end of this firing rate coding stuff. I just did some simulation to show you that. So the black one, it's the place cell system adaptive code with the half circle. You see the reaction time is really decreasing like 1 over n rho. So that's what I told you. This is the random code. The random code for place cell also, okay, it's random, but still it looks like a 1 over n rho. We tried many grid cell systems. All of them have the same problem, is that they are stuck at one value. So in this sense, because they seem stuck at one value, you cannot go faster when rho decrease, but we don't know how to prove that in general. So to finish, so first, so that's the firing rate period. So that was also what I did yesterday. That's the conclusion for both parts. So what I showed you so far is that you can detect when a cell is firing rate coding. It's kind of easy, the test to do that. Now you go to the brain interpretation, and what they have done so far was with Fisher information, and we don't think it's the best way to understand what's going on. So we decided to test pairs of position, and for that we have shown that there are advantages and disadvantages of both systems, place cell and grid cell. So place cell, they cannot discriminate at a shorter range than 1 over n, but they can be adaptive. So in this end, once you have passed the 1 over n, it's possible to, with the same system, to go faster when the things to discriminate are further away. That's what I'm saying here. Adaptive place cell codes exist. The minimax and adaptive properties of grid cells are computable if you fix the size of the module and the scale, the period. But if you don't have that, we don't know if it's possible. We know that the extreme DID call is reaching the rate 2 to the minus n. So in terms of precision, that's the best code you could hope for, because that was the lowest bound for any kind of code, not only place cell or grid cell family. But they cannot improve when the distance increases. And we know also that it's possible to achieve a better rate than 1 over rho n, which is log of 1 over rho divided by n, which also explains why you find a limit rho, which is an exponential over n, right? It's linked to that. But again, we don't know if it's the best if something adaptive is able to do that. And we don't think it is possible, but I don't know. So there is a lot of open problems, and in particular, well, of course, minimax and adaptivity for general grid cell when the number of modules, the periods, and ni are let free, we don't know. Well, that's my stupid interpretation as a non-neurobiologist, and I need to discuss it with neurobiologists, but it's possible that the two systems exist in the brain because they have advantages and disadvantages. Like the place cell, okay, it's not as precise as grid cells, but it allows you to have faster reaction time when your distance is increasing. So maybe you have a switch between both systems depending on what you want to do. And I have to discuss that with biologists. Also, we did it only for circular maze in 1D. We don't know about the 2D problem, especially the fact that grid cells are in triangular grid. We don't know how to do computation with that. Also, the real grid cells, the size of the mesh is not an integer value stuff. I mean, the ratio even between mesh is not an integer, which is very different from what we have here. And we don't know how to make the computation if we don't have this interpretation that one module is taking charge of the modules that are smaller than what it is. And yeah, of course, we would like to go beyond the two-value codes. In the exercise, there is this exercise about a continuous Fi of S, but for the estimation problem with Fisher information. Can we do that for testing? Probably it's the same kind of computation, but it's just more intricate. Okay, that's a small reference. Also for the people who want to know more about multiple testing, it's here. It's a very good review by Etienne Roquin. And I will put the slides on my webpage, maybe just after the conference, because I don't have the access code for it from here. I'm not sure, but I will put them. And do you have any question on this part before I go to the next part? No? Okay, okay. So now let's talk about synchronization. So we are here. So that's the third part. So we worked with a lot of people, and Eva, and Josué, who is here. But most of the thing I will talk about is the work of Mélisande, who I had in PhD thesis with Magali Fromont. And she worked a lot on bootstrap for endpoint processes, and that's what I'm going to explain right now. And of course, we applied it to the maze, to the right in the maze. So at the end, there is always all the same guys as before that were there for the experiment with the rats. Okay. So far, we have done as if the neurons were not connected in your brain, but it's not the case. They are connected. And you remember how it works. It works when this one is sending a spike, it modifies at the synapse level, it modifies the membrane of the voltage, and so you have a kind of summation, and you reach a certain threshold, or you're just more excited, and at one point you spike because your voltage is too high.
Yesterday, Sandro had doubts about this moment to us. Sandro, here's the picture of doubt. This is the picture you have.
Yeah, it's a very schematic picture. Okay. It's not the truth. It's just to make you understand what's going on. Okay. And especially for that. So now if you imagine that, okay, this guy is also connected to this guy. And so if they fire at exactly the same time, or if they manage to have their spikes arrive at the synapse at the exact same time, then of course, because they are arriving at the same time, you will reach more rapidly the threshold. You will not have the attenuation phenomenon, so probably you will not use as many spikes to transmit the information. So synchronization could be a way to transmit information more effectively, right?
How do you define synchronization?
I arrived there. Okay. And people have thought, I remember we are looking for codes. So there was a firing rate code. And people think that synchronization, if we can detect them, would be a part of the neural code, and after that we could analyze it as we have done for the firing rate coding. Okay? Okay, the problem is how we define synchronization, because we don't see the voltage trace, so we only see that, so we have to define synchronization with that. Okay, so what do we do? Okay, so we are going to say, so here you have the spikes of N1 and N2, and you fix a small size delta, imagine, I don't know, 10 milliseconds. And you are going to count what for the moment is called a coincidence and not a synchronization yet. Coincidence is when those two things happen at the same time, or roughly at the same time. It's like what you are saying, a coincidence in real life, okay? If you want to have a formula for it, you can write it like this with the point measure, okay? It's obvious for everyone what it means, or you want a summation? No, it's fine now? Okay, now in fact synchronization becomes a testing problem, because we are going to speak of synchronization when this count is too large. And too large with respect to what? That's the big question. Okay, just...
Could imagine this means that 1 neuron not of one, really you're suggesting.
Yeah, it could be, or that they are arriving at the same spot. And that's, I don't know. But at least they are not independent. Yeah. Okay. So the main question, so we are going to want to, in fact, test that H0 N1 is independent from N2 versus H1 they are not. And what we are going to count is this coincidence count. Okay, and we are going to reject H0 when C is too big. And for that, we need the distribution of C under H0. Okay, so this afternoon, I hope you will do at least the first exercise. So in the first exercise with Sophie, you will look a bit at that. Okay, so because you assume that they are Poisson processes, you can compute like its expectation, its variance, transform it into, if you have n independent trials, yeah, you have always n independent trials, IID. And you have access to the distribution of the coincidence count under H0. We will not do it this afternoon because it's a bit technical. So this afternoon, you will assume that you know the firing rate lambda 1 and lambda 2. And you can do all of that very easily. If you don't know them, you have to plug estimator in, and then it changes the variance. Okay, but it works. Problem is that you are assuming your spike trains are Poisson. They are not Poisson. That's what already Eva told you. We have assumed it's Poisson before, but we would like something that does not assume Poisson, because at the same time we want to detect something which is a network thing. So they are clearly not Poisson because this is inside the network, and we are using the Poisson assumption, so it's weird, right? So what we did was to bootstrap the distribution. And I want to explain a little bit what it is before moving from there. So, does everyone knows about bootstrap and bootstrap of the mean, or you want me to repeat? Okay. I repeat, yeah, a bit. What is important to know? So imagine you have y1, yn, they are IID. With that, you compute y bar, okay? And And in fact, you want to make, well, either tests or confidence interval or whatever on y bar. So you would like to know the distribution of y bar, but you don't know it. Okay? Some people have said, and that's basically Efron's bootstrap, that you can pick at random new observation that would be like, how can I say, observations that are made by your computer that will be there just to make you guess what is the correct distribution. Okay? How you do that? You are going to sample yi star. It's what is obeying the distribution, which is 1 over n, the sum of I equal 1 to n of the direct in yi. Okay? So it's like I'm doing this in an ID way. So I have y1 star until yn star. And of course, I can do that many times. Okay? So I can do that in a loop like b times. And of course, for each of them, I could compute this thing, right? The basic bootstrap that does not work is to say, okay, I do that b times. I have like an empirical distribution for that. And this empirical distribution should be the distribution of this thing. It's not working because bootstrap is a second order property. It works as the TCL works. So if you don't use it to centered quantity, it's going to have a bias. And the quantity you are estimating by doing that have some problems because of that. So what in fact you want to bootstrap, so we want to bootstrap y bar minus the expectation of y, okay? And eventually we put a square root of it. We know that this thing, because of the TCL, is going to tend towards something distribution when n tends to infinity, right? And in fact, the only real big thing that is problematic for us is that we don't know sigma to make the whole thing works, okay? And what, in fact, Bickley and Friedman proved for the bootstrap of the mean is that the good quantity to put here, okay, again, you do the bootstrap sample, but now you want to have the estimation of that given the original sample, okay? If we do that and we put again the square root of n, you can imagine that this thing, even, so it's a word given, okay, given the original data, this thing in a normal surely matter given the original data, because you picked n and id variable at random, it's also going to tend towards a Gaussian variable, which hopefully will have the same mean. In fact, it's even better than that, because you can prove, it's what's called the second order property of the bootstrap, that this conditional distribution is going to be closer to this one than the limits that they both have, that they share. So what is important to understand is that what we need to bootstrap to get a bound distribution for my coincidence count is not the coincidence count by itself, it's a centered version of this coincidence count. Because I will need to center this thing to make the bootstrap work. Okay. So what we did was to say, okay, so yeah, maybe I could think phi of n1, n2, okay? Going to have, I hope I'm not, I have to be careful where are my indices. So I am given n1i, n2i. For I equal 1 to n, there are IID couples of spike trains, okay? Because I have n trials of the same thing. You will see an example just after that. Imagine you are asking to the animal to repeat the exact same thing several times. Okay, from that, you can compute phi of n1i, n2i. You could sum it. You could divide it. But this is not centered, right? So what we are going to remove is n to j. And here I'm summing over all I So it depends, but it's, I think, I different from J. Because when I do that, I'm really centering by something which looks like the expectation that this would have given the sampling that I'm going to do. And so this is my, I have n-1, and this is the U statistics that I'm going to use. Okay? And because this thing is centered, we have been able to prove. So there are various ways of bootstrapping. So either we are saying the first bootstrap is F1 bootstrap. In F1 bootstrap, you are saying that you keep an I1 with the same I, and here you pick, let's say, a J star, where, how can I say, J, yeah, G of I star, where G of I star is taken uniformly in 1n, and the GIs are IID. Okay? So I'm replacing my original sample, which is this thing. Okay? So let's call it xn, with this bootstrap sample, which is xn star. Okay? Maybe I have a picture for that to be sure you understand. Yes, I have a picture. So those are my 3 here trials. So the full bootstrap here is going, I'm picking the second one at random. So for instance, here I'm picking the red, so I can have 2 guys that are in the same trial originally, but I can put another guy here or another guy here. And I'm going to, for instance, here, what did I do? Yeah, it's the first that is moving. It's the first that, I think this one has to be green, sorry. I made a mistake. This one is green. So the second one is picked at random. It can be this one. You can have repetition, so you have 2 times the same second guy. And you pick eventually the third guy. And eventually you never picked this one, which is the green guy of the second trial. Okay? So that's the first bootstrap. You could also do permutation. In permutation, you are not repeating information and you are not losing information, meaning you can put here, if you pick the random permutation 2, 1, 3, you put the second trial here for the second neuron. Here you put the first trial, and here you leave it in non-change. People in neuroscience thought it was weird to allow that sometimes you have exactly the same trial together in the bootstrap sample. So they forced it to not be on the diagonal, but you can have repetition. Okay? All of that is just a way to understand how you pick the second coordinate and compute what is your U star. Okay? In all this setup, you can prove that the Wasserstein distance between the law of square root of n, U, and star, given the original sample, and the Gaussian variable with the variance which corresponds to the independence between the 2 coordinates, this thing tends almost surely to 0. Almost surely, or in probability? In probability, sorry, to 0. Okay, so even in this weird point process case, you can prove that you have convergence. So we need that it has, that the expectation of nt, well, the number of spikes to the power 4 is finite, I think. And I think that's it. We are not assuming it's IID, sorry. We are not assuming it's stationary. We are not assuming on the trial, okay? We are not assuming that they are Hawkes processes or whatever. They can even be non-continuous with respect to the Poisson measure. You could have direct masses at some point. All of that is allowed. What is important, in fact, is that this function, and that was a tough job for Mélisande, is continuous in the score space and to make all those limits work.
You make an assumption of the coupling between the two.
No.
If you assume that this has a property,
We assume that
and two have some certain property as coupled in some way.
No, exactly.
well, in H0 they are independent, right?
I assume they are independent. Okay.
What we have proved is that even if we are under H1, those bootstrap procedures are giving you the Gaussian distribution with the independent variance. And in this sense, you can use them as for critical values to make the test. Okay? But really, except finite moment, I think we have no simple. We don't have to point at the same place. But except that, yeah, almost nothing. Another important point, yeah, so that's what I'm putting here. So, as I said, it's important to know that if you want it to work, sorry, it's in green. I read it. You need a correct centering of the statistics. That's what we are using U statistics. Because if we don't, you have a problem with the bootstrap that is not centered, that is going to make it bad. And people in neuroscience have used it with a bad centering. Well, they didn't center at all. And sometimes they were finding stuff that they shouldn't find, and it's just because they were not centering the statistics. And they interpreted it a lot, but you have to be extra careful with the centering of the bootstrap to make it work. And then I want to explain a little bit why permutation offers more. So the permutation case is a bit particular because you see when you are making permutation, if you are under H0, those variables, they are exchangeable. So because they are exchangeable, you don't even need to be at the limit to define the good p-value. So in fact, and that's what people will show in the exercise either this afternoon or tomorrow, I don't know, is that if you take a permutation, so it means now that you are coupling Ni1 with Npi2, where P is a uniform permutation on 1n. Okay? And so you do that for P1 until Pb. Okay, so you draw at random B permutation. Okay. Each time you're going to have a coincidence count. So you're going to have a coincidence count for P1 until a coincidence count for Pb. And you have also another coincidence count, which is the one that you have observed. Well, from that, you can compute a p-value. And your p-value looks like that. It's 1 over b plus 1, 1 plus the sum for I equal 1 to b of the indicator then Cp1, pi, sorry, is bigger than Cops. So if you think about it, what you are if you were imagining that F1's bootstrap was working even if it's not centered, the only thing that you are saying is that I have a random distribution that I'm computing with that. This is my empirical bootstrap distribution. And my p-value is the number of these empirical values that are bigger than my observation. Okay? And if it's super small, it means my Cops is super big. So this should be a p-value. You have to add a 1 because, in fact, this guy is just one of them under H0. And then, in this framework, they are all exchangeable. So you can prove that the probability under H0, because they are exchangeable, that your p-value is smaller than alpha, is always smaller than alpha. So this thing is a p-value, even non-asymptotically, even without centering, even without nothing, it's a p-value. And so we are going to use that in practice because we have something which is non-asymptotic. Also, it's possible to prove that even if it's written like that, in fact, making it on C or making it on U, which is a centered stuff, is the same thing, which means that this test with these p-values is equivalent to the test on the U with the one that has a good asymptotic distribution, which means that you win on both sides. Like, you know that you are performing a good approximation of the distribution, but at the same time, thanks to this +1, and it's really funny that you need this +1, but you need this +1. With just this +1, you have something which is a true p-value for all B and N. You don't care. Okay. So with that, what can we do on real data? So the first thing we can do, so it's an experiment on monkeys. And those monkeys, they were in front of a screen. And they have been taught that this screen was going to be, so the screen was red at this, so this is time. Here the screen is black. Here the screen turns red. When the screen is going to turn green, the monkey is allowed to touch the screen and then he receives a drop of juice. Okay? And during the experiment, there was only two possibilities for turning green, either here or here. But here you have only data where the screen turned green here. So the furthest, the longest data, okay? Except that the monkey knew that there was two possibilities. Here is the times where it teaches the screen. Of course, it depends on the trial. Here it's when it receives a drop of juice. Here it's your first neuron. Each of the line, it's a trial. Here it's a second neuron. Each of the line is a different trial. And here it's a couple of neurons, and here it's another couple of neurons. So let's focus here. Here it's the ghost signal. The monkey knows that something is going on here, but if you are an outsider, you don't see the monkey moving, you don't see anything on the screen, so officially nothing is happening. Except that if you make this permutation test, p-value, on sliding windows like that, and you correct for multiplicity by Benjamin-Hirschberg, you see that this window and this window, you are going to have more coincidence than what is expected by the bootstrap distribution, meaning you have synchronization between the two neurons. Meaning that somehow, with my very basic and probably for Daniel too pushy interpretation of it, it's as if the neurons were going to synchronize to make the action faster because maybe something is going to happen. Nothing is going to happen, he stops, and he goes back to that a little bit later. Of course, not all neurons can synchronize. So in fact, if you have other pairs, you see here anti-synchronization. Because with the same distribution, you can reject when you have too much coincidence or not enough coincidence. And in fact, here you see this is a period of space where you have a lot of spikes, but they try to avoid each other to have less excitation in the system to balance that some of them are doing that. And so what you see is that now, if you remove the math from the equation, the monkey is anticipating that something is going to happen at 600, well, at the blue signal here, that the spike trains that you have are not independent, which is everything that I told you before. So everything that I told you before, you can throw it away, not completely, but still. And it's really as if you have access to a code inside the brain saying that he knows that something will happen at 600 milliseconds. Okay? Okay, and now let's go to the rat in the maze. So for the rat in the maze, maybe I make a picture again of the rat in the maze, just to be sure you remember. So you remember that was this maze like that. And so there were two crossroads. I think it was B and A like that. Maybe it was the other way around. I'm not sure. So what we did is that each time the rat was crossing that, it was a trial. Okay? And so we consider every pairs of neurons that have been recorded on the same day, and we made this synchronization test to see if there is something going on, like a synchronization here. The problem is that if you correct by Benjamin or Hirschberg, you are not going to detect anything. There is not enough information in your data. But we can do something else, which is called p-curve. And in fact, it has been invented by psychologists, but I think it's such a nice idea that I don't know why statisticians are not doing that. When you get p-value, you know that if your p-values are under H0, the CDF of the p-value should be smaller than the diagonal. Why? Well, it's because of that. This is my definition of the p-value, okay? So it means that if I picture the empirical CDF, if all my p-values were under H0, I should have something like that. Maybe it's not equal, especially in this case, because they are going to be discrete, okay? But they have to be smaller, because this is what it says here, right? Okay, so now if I picture the CDF of the p-values of what's going on at those crossroads, yeah. Sorry. So those are my p-value, and this is 0, 1, and this is the CDF.
CDF of what?
Of the p-value. Well, this is a true CDF, and now this will be the empirical CDF. But yes, this is this function, right? If you are under H0, you should see that the CDF of your p-value is below the diagonal because you have that, which is always true because it's a p-value.
They are not uniform.
On the experiment, they will not be. But if they were under H0, that's what I will show just after I press the button. But you see, that's what it means, right? This is the, if you assume that this is your random variable x, what I'm computing here, it's CDF. And by definition of my p-value, this CDF has to be smaller than alpha for all alpha, meaning that the CDF is below the diagonal, right? And so if you don't care about pinpointing what are the couples in your population that are dependent, but you just want to find out if there is any synchronization phenomenon in all the pairs that you have seen, you can just plot the CDF and see if your CDF is going to be like that, okay? And if it's really above, with a Kolmogorov-Smirnov test, for instance, one-sided. I don't know who asked me about one-sided, for instance, here. You're really one-sided. You are going to know if in your population there is synchronization or not, without being able, as with Benjamin Hirschberg, to know which one are coding or here synchronizing. Okay? So that's what we did. And what is super fun is that at B, so yes, I think it was above, so it's at B, you have that the DMS is really significantly more synchronized than the uniform. These are the p-values of the Kolmogorov-Smirnov test. And also you can compare CDF of p-values to see if you have more synchronization in dorsomedium striatum with respect to dorsolateral striatum, again by Kolmogorov-Smirnov. And you can prove that at stage 2, between the DMS and the DLS, you have more synchronization in the DMS than in the DLS.
DMS is the routine?
No, it's the other one. And we are in stage 2, so it's when it starts to learn, and they are synchronizing at that period. Okay?
How to choose delta?
What is delta? Huh?
Is more.
Yeah, so usually it's 10, I think, yeah, I put 10 milliseconds. There is a range. When people do this analysis, it's usually between 5 and 20 milliseconds that they are looking at. Most of the time, they are looking at several at the same time. Here, we choose just one, and I think I took 10. I don't remember exactly. But it's a few milliseconds, so it means that typically, if they were directly linked, it would be a gap of 3 milliseconds. So it could be like you have 2 or 3 relays between the 2 neurons, and that's it. Okay. Just because I think the story is super fun. So they called it p-curve. In fact, it's a p-curve. What I'm plotting here. In fact, what they called the p-curve was the histogram of the p-value, and they were trying to find if the histogram was flat. Except that an histogram, it depends on the size of the bean, etc., etc. Whereas, in fact, if you just integrate, you don't have to even think about that. But their p-curve was the histogram. And the story about that is very nice because they are psychologists, and they said that there is too many results in neuroscience that are not published and that are in the file drawer, because when you correct, you don't find, for instance, here any pairs that are significantly synchronized. But if you look at all the experiments that have been done, then you can see in the population that there is something going on, even if you cannot pinpoint what is the experiment that worked. And so in this sense, they said it's a key to the file drawer because it's a key to understand what is in all those unpublished results that they have in every neuroscience or psychology lab that you could use by just plotting this kind of curve and seeing if there is something. So, okay, that I thought was nice. And I think I'm done. Yes, for not tomorrow, for Thursday. It's just an introduction for Thursday and the conclusion of today. First of all, you see that if you remember the story of the monkey, we picked two neurons in the, here the motor cortex. Those two neurons, they are probably not physically connected. There may be, because especially I took a distance like that, there might be a few relay in between, we don't know. If you remember again the neurons, you see that it was super fast, like it was not synchronized, poof, it was synchronized, go back to non-synchronized, poof, they are synchronized. So it's not as if the physical connection in the network changed in a few milliseconds. It's not what's going on. It's just that there are other mechanisms hidden behind in the whole brain that is changing the activity of these neurons that are making them synchronize at one point and desynchronize at another point. Okay? So, in fact, this depends on the cognitive process at play behind, and it's a kind of, I really liked your talk yesterday. It might be like a kind of projection on what we see on those two neurons of the whole system, and this whole system is telling us that, okay, the dependence change, might be a part of the neural code, we don't know, but it's changed super fast, and this is a mark of everything that is not recorded inside the system. Okay? Also, something important because it's tomorrow or it's tonight? Tonight. Josué will have a poster, and it's super nice because it's a link between today's talk of Eva and mine, because he will see how this synchronization test applied to Hawk's network in a homogeneous interaction network. We have seen this morning with Eva that when m, the number of neurons in the homogeneous network, tends to infinity, the neuron decorrelates. So, of course, at one point, this test should say there is nothing to see, right? And the question is, when are we able to detect that it's really an homogeneous network that is connected, and when do we think it's just independent Poisson process and we don't see the difference? And so we made all this computation, and he has this nice poster tonight. So I'm making an announcement for that. And last thing, and it's for the course on Friday. So what we'll see on Thursday is how we use Hawk's processes to combine firing rate and synchronization and eventually decode. So really go to the coding of the network instead of coding of a neuron. But then all of that, as you have seen for the monkey, it changed super fast. And the fact that it has changed is because the network has learned. And we will speak about learning on Friday. That's it. Okay. Next question? No?
¿Quién? Ah, sí, Alex. Sí, Alex. ¿Están sacando fotos?
Gracias por avisar.
Sí. Miremos, ay, qué feo, queda feo mirar la cámara, no. Queda muy feo ver que te están sacando una foto. No. Bueno, yo lo voy a leer lo que escribí porque no me va a salir nada si no lo leo.
Pablo, ¿aplaudimos? Okay, welcome back. It's a great pleasure to introduce our next speaker, Florencia Leonardi. Here.
Okay, thank you, Ines, for the introduction. So it's a pleasure and an honor for me to be here in this EBP. I wrote something about. I think I'm going to read because my English is not so fluent, so it's easy to read it. So it's an honor, as I said, it's an honor to be here in this EBP in honor of Antonio. So Antonio, I don't know if everyone knows, but Antonio was my PhD supervisor. I met him in 2004, and I was his student in a course about inference for stochastic processes. And at that time, I was enrolled in a PhD in bioinformatics. And at that time, I was working in another group here at IME. And as a requirement for the PhD, I did this course. And the course was really extraordinary. At that time, Antonio had begun to work with processes with with memory of variable length, and was analyzing the codified data of Portuguese written text. So in the course, we studied articles about the subject, we did simulations, we tried new models. It was a very nice experience. And at the end, Antonio and Pablo was also organizing GBP and inviting me to participate. So after coming from the EBP and in Maresias, I was sure that this was what I wanted to do. And I decided to change my PhD project and to begin to work under the supervision of Antonio. So I need to say that this decision was not easy, and was not easy also for Antonio because he was not part of the bioinformatics group of supervisors at that time. And we needed to find another supervisor from the area of biology to certify some way the project and to convince people that we will do something new in bioinformatics using the variable length processes. So Antonio was very generous in challenging this with me and helping me to conclude this PhD. So I am very grateful to him for that. I think he has always been an inspiration on how to challenge new problems and how to escape from the comfort line. So if we see the different problems Antonio was working on in his career, we can have a strong evidence about that. So thank you, Antonio, for your inspiration and your guidance. It really made me a difference. So after this introduction, so in this talk, I'm going to talk about optimal recovery by maximum and integrated conditional likelihood in the general stochastic block model. So I would try to do an introduction about this subject. Sorry, sorry, I read what I wrote. I forgot to show the pictures. Okay, these are pictures of my PhD defense, were the only pictures I found. So, and this was the jury. Many of them are here. So this was the NUMEC that was, I think, open at that time, maybe 1 year after my defense or something like that. The NUMEC was very new at that time. So here is Roberto, Nancy, Antonio. This is Hugo Armelin, my PhD co-advisor, Hugo Armelin. This Ricardo, Pablo, and this is a professor from the Institute of Chemics, Chuck Farah. So this was the jury of my bioinformatics PhD. So, okay, so let me talk about the stochastic block model. So the stochastic block model is a probabilistic model for a random graph whose nodes are organized into blocks or communities. So suppose in general we observe a random graph like this, but the idea of the stochastic block model is to trying to see communities, because many real networks exhibit some community structure, like this one. And so people thought about this model as a model for communities. And this model generalizes the Erdos-Renyi random graph model, which is a particular case with a single community. So we are going to see how is this generalization. And, okay, sorry, I passed. Okay, sorry, it's not working. Let me see here. So much interest in the community detection problem. Analyzing these networks, people has much interest in the community detection for a fixed number of communities with many recent advances. So in general, people observe one network as this one, where you don't see any community structure, and what you want to detect is the groups. So you want to detect the communities, assuming you know the number of communities. So in general, people assume there are, say, 3 communities, so you try to group the nodes here to find these communities. This is what is known as community detection. So how the model is formalized, how is the formalization of the model? In general, you have 3 parameters. K is the number of communities, pi is a probability, a discrete probability on k labels. So the labels are this one. For example, you have k label for the node, so 1, 2, k, and each node has a label in this set. So pi is the discrete probability giving you the probability that a given node is from the community J. It's only a discrete simple distribution. And then, so in each node, you assume you have a variable Z indicating the community of the node. And then, once you have the communities, you will put an edge between 2 nodes. Here, you will put an edge between the nodes I and J with a probability that depends on the labels of the nodes. So, for example, if you have 2 nodes here, Z1 and Z2, and the nodes are from communities 1 and 2, for example, okay, this is nothing to do with the index here. Suppose this is from community 3 and this is from community 4, you will put an edge with a probability that depends on the specific communities 3 and 4, for example. And the edges are independent of each other. So, why this is a generalization of the Erdos-Renyi model? Because in the Erdos-Renyi model, you don't have communities. It's like a single community. You don't have this probability. So each node acts the same as in the same way, and you only have a probability of having an edge in the Erdos-Renyi model, and the edges are independent. One is independent of the other. So here you have the same independence assumption, but you don't have the same distribution for the edges. So the distribution of the edges depends on the communities of the nodes. Okay. So it's a very simple model, which have the only difference with the usual Erdős-Rényi model is that the nodes have a specific community label given by this probability pi. So the parameters are this k, pi, and the probabilities of having an edge between the different communities. So this matrix is symmetric because the order is not important. If you have community 3 and 4 or 4 and 3, it's the same. So these are the parameters of the model, okay? It's not working. What, the P? No, it's not a stochastic matrix. These entries are positive because they are probabilities, but they not need to sum 1 because, let me see, they don't need to sum to 1 because they are independent one of the other. Let me see what happened, I'm not sure. Okay, in general, okay, I didn't put it here. You observe a network with n vertices, so n, I didn't put here, so n vertices. And in general, you study the behavior when n goes to infinity, okay? When n diverges. But we don't have any, and we're going to see some specific cases where these probabilities depend on n. What happens when these probabilities depend on n, on the number of vertices? So we assume n, small n, is the number of vertices in the network, okay? So what happens is that the model generates you a network like this one. When you generate the network with the model, you can see the labels of the nodes and you know the communities and all. But what we assume from the statistical point of view is that you observe this network. So you assume you have a network generated by this model, but the labels are removed. So you don't observe the labels. You only observe the edges, the nodes and the edges, and you will try to detect the communities from this network. So it's like a hidden process in some sense because the labels act as hidden variables, latent variables. Let me see. Okay, this is not working. I think it's going to. So what happened with the different? What happened with the different? We have different regimes for the P matrix. So assume all the entries of the matrix P, the probabilities of the edges, are bounded from below by a positive constant. So in this case, the graphs, the networks you obtain are dense networks because you have linear degree regimes, because each node has this positive probability of connecting to any other nodes, and as you have n nodes, you will have linear degree for each node. So this is not an interesting situation because in general the networks you observe are sparse. So this is not a very interesting situation. So in general, people study the situation where the probabilities goes to 0 with n. So the probabilities are model are of the order rho n, where with rho n is a parameter that goes to 0 with n. So in this situation, you obtain sorry, it's not working. In this situation, you go from semi-sparse to a sparse model, and the degrees of order n rho n. Okay, because rho n is the probability, and rho n is the degree, the mean degree of the nodes. So, if we assume that all the entries of P are the same and equal to P, so the SBM, the stochastic block model, collapses to the Erdős-Rényi model with n nodes and this probability P. So there are some results from the usual, from the classical Erdős-Rényi model that are interesting here. We know that if the probability P is of order C log n over n, then the graph is connected with high probability if and only if C is greater than 1. So this is a basic result of the Erdős-Rényi model. And if you have the probabilities of order C over n, then the graph has a giant component that is a component of size, of linear size in n, and also if and only if C is greater than 1. So this behavior, we can extend this behavior to the stochastic block model with k communities and with probabilities of this type. So assume the probability of connecting nodes of the same community is A times rho n, and of different communities is B times rho n. So in this case, you will have a matrix like this. So in the diagonal, you will have A rho n, and of the diagonal, you will have B rho n. In general, people assume that A is greater than B, so you have more connections inside the same community, but this is not, this can be relaxed. But suppose you have this matrix, then if you take into account the mean degree of each node that is given by this expression that depends on k, the number of communities, then when rho n is log n over n, the graph is connected with high probability if this mean degree is greater than 1. So this is an extension of the results for the Erdős-Rényi graphs. And the same happens when you have rho n 1 over n, so the graph has a giant component that is a component of size linear in n if and only if this mean degree is greater than 1. So what happens is that, okay, we will see that, what happens is that this condition, so what we have is that this condition is necessary to have the exact recovery of the communities, because you need to have a connected graph in order to detect the communities. If you don't have a connected graph, you cannot detect all the communities of the label. So this is a necessary condition, and we will show that we also need other requirements to have the exact recovery of the communities. So what is, now I'm going to talk about partial and exact recovery of the communities, the different notions of consistency you can have in this problem of detecting the communities. So suppose first you have an estimator of the community. So an estimator of the communities is a vector of size n in this set, because you want to identify the label of each node. So you have a vector of length n with taking values in this set, 1k. So this, suppose you have an estimator, this is the estimated communities. So you want to measure the difference between the estimated vector, the estimated communities, and the true communities. So suppose the n here are the true communities. So we simply count the difference between these two vectors. But what happens in community detection is that as these are hidden labels, latent variables, you will not be able to identify exactly the communities, because any permutation of the labels, so you are going to detect the groups. You can detect, for example, if you have a network, okay, you can say, okay, this, no. Okay. Okay, no, I'm not going to. I'm not sure if this is better. Here is yellow, Yellow? Okay. Okay. So suppose you have a network and you need to detect the communities here in this network. You will be only able to say which are the groups. So for example, you can say, okay, these nodes are in the same community, these nodes are in another communities, in another community, and these nodes are in the third community. But I cannot assure that this is the community 1, this is the community 2, because the labels have not any meaning, have no meaning for us. So, so we can only detect the groups. So the notion of discrepancy between the label has to take into account this situation. So the discrepancy for us is the minimum between every permutation of the labels. So you consider any permutation of the labels and you see which of these permutations have less discrepancy with your vector of true communities. So sigma here is a permutation of the k labels. But this is not a problem. So you can only distinguish the groups and not the exact labels. So the notion of partial recovery is that this discrepancy measure will be sublinear with high probability, with probability conversion going to 1. Okay, so this is what is known as almost exact recovery or weak consistency. Sometimes also partial recovery. Okay, there are many names for the same thing, but in this, with this notion, you are saying that you are detecting an increasing proportion of labels. Okay, so this is weak consistency for an estimator. And we also have another notion of a strong consistency here. What? Yeah, it's missing, but here is when n goes to infinity, okay? So, yeah, this arrow means that this probability is converging to 1 when n goes to infinity. Yes, sorry, I omitted this detail. So for each epsilon, the proportion of misclassified labels is sublinear. So with probability conversion to 1 when n goes to infinity. But exact recovery means that you can recover exactly the n nodes, so you have 0 misclassified nodes with a probability going to 1 when n goes to infinity. Okay, so these are two notions of recovery for this problem.
Change the arrow and the equal sign, the plus the question.
Here? Yeah. Why?
Because the convergence is equal to 1.
No, the limit.
No, this probability converges to 1, but with the event is that you have no errors here. The event is you have zero errors. What?
Some fixed n.
No, the probability. The probability of this event goes to 0, goes to 1 when n goes to infinity. Okay, what? Yeah, the limit is okay. So sorry, it's not. it's confusing. Yeah. So let me write. So the limit when n goes to infinity of the probability of the discrepancy. Exact recovery is that the probability of recovering all the nodes, so having 0 errors, this limit is 1 when n goes to infinity, the limit of the probability, okay? So, as I said before, if the graph is not connected, exact recovery is not possible because you cannot detect all the nodes in a disconnected graph. So, a necessary condition for exact recovery is that this rho n parameter is at least log n over n. Okay, so the probabilities can decrease to 0 at least as log n over n to have exact recovery. And we have other conditions also, not only this one. Okay, so in this case, a specific case of having only two parameters, A rho n for the same community and B rho n for different communities, the requirement to have weak consistency or partial recovery is that n rho n goes to infinity. Okay, this is for weak consistency, it's not the same as here. For weak consistency, to detect only a portion of the nodes, we only need n rho n going to infinity. So this is a result of Mossel, Niemann, and Sly in 2016. These results here are for the planted bisection model, that is the model for two communities. So when you have pi equal 1.5 and 1.5, so two equal size communities, and a matrix of P, P, Q, and Q. Okay, so a model for only two communities. This is known as planted bisection model. And when you have rho n equal to log n over n, and this condition on the coefficients of the probabilities here, here, maybe I write it as A log n over n, A log n over n, B log n over n, and B log n over n. So when you have this rho n and this condition, a specific condition on the coefficients, you have a strong consistency. So it's possible to have a strong consistency, and this is a result obtained independently by Mossel, Niemann, and Sly, and also by Abbe, Bandeira, and Hall in 2016. But so these results were specific for the model with two communities, and assuming that the parameters were known. So in general, in these works, people assume you know all the parameters. You don't have to make inferences on the parameters, and you only have the problem of recovering the communities. So when we go to the general model with K communities, okay, there are no specific results about almost exact recovery, but we can infer that the same condition applies. N rho n going to infinity allows you to infer almost exactly the communities, because you can think that you can detect a partition in two groups every time until you recover all the communities. But there are no exact results about this, or specific results in the general model. And for the degree, okay, for this condition, in the case of rho n log n over n, you have exact recovery with a condition like this one. Is a little complicated to analyze this condition. This appears in a paper of Abbe and Sandon in 2015. So this is a general condition on the parameters of the model with K communities. Here appear in P and the probability P with this rho n to have exact recovery, but also assuming they know the coefficients. Okay. So work, in the results I'm going to present here, we studied with Andresa Cerqueira, that is a professor at the Federal University of São Carlos. We studied maximum likelihood and Bayesian estimators for this problem. So from the statistical point of view, in general, people study the maximum, the classical estimators are maximum likelihood estimators. So what happens in this case with the results about the degree of the network? In this case, in the case of these estimators, so first I'm going to introduce some notation to define the estimators. Here you have the network. These are the Z are the latent variables of my nodes, and this is the representation of the network with the adjacency matrix. Okay, so the adjacency matrix is a n by n matrix with zeros and 1, where you have a 1 when you have an edge between two nodes. So if you have an edge between the node I and j, you have 1 in the adjacency matrix. So this matrix is symmetric and have only zeros and 1. Okay, so this is the form of codifying the network. So when you have this network, you can define this matrix. You can define the conditional likelihood of seeing this network given these communities. And this is given like by a Bernoulli, usually like a product of a product of Bernoullis, because they are zeros and 1, so you have these parameters, and this is a product of Bernoulli's likelihoods, where you only need to count how many times you observe here. OAB is how many times you observe an edge between the communities A and B. So these are counters from the network. So you count how many times you see an edge between community A and B, and here you count how many pairs you have between communities A and B, and how many of such pairs are not edges. So you subtract the OAB, and you have the form of the likelihood for this model. So in a maximum likelihood estimator, you use this likelihood, and then we take the logarithm of this function and we plug in the parameters, because in general we assume, in statistics we assume we don't know the parameters, so we don't know the probabilities P. So we estimate the probabilities by maximum likelihood and plug in the estimators here in this expression. So when we do this, we obtain an expression like this one, depending only on the counters of the network. And for this function tau, okay, this is a specific function. So we have an explicit expression for the maximum likelihood of the maximum likelihood of the network given some labels. Here you see this depends on a specific vector of labels. So this is the maximum likelihood modularity defined by Bickel and Chen in 2009. So this modularity was proposed by them, and so the estimator of the communities based on this modularity is to take the argument of the maximum of this function. So we maximize the modularity, the likelihood modularity over Zn, and we take the Zn that maximizes this expression. So this is the estimator of the communities based on maximum likelihood. Okay. And here we are maximizing this function over a special set of vectors, because we cannot maximize overall the space, because in general we expect to have linear size communities. Okay, we have k communities, so each community is linear in size, because you cannot have sublinear communities, because if not they eventually will disappear. So we are considering that we are maximizing this likelihood over linear size communities. Okay, so this is only to to emphasize this. So for exact recovery for the maximum likelihood estimator, we have this result of Bickel and Shen of 2009, that you can have exact recovery under this condition of rho n being of bigger order than log n over n. And they have, in some sense, an incomplete proof because they assume many hypotheses that were not checked in practice and that they were, in some sense, wrong without all the verification. So, so they do not obtain the minimal rate for have the exact recovery in this maximum likelihood estimator. And there was another approach from the Bayesian point of view that was the same idea, so to maximize a modularity. And the modularity was a Bayesian modularity with prior distribution. So we take some prior distributions over pi, that was a Dirichlet, and over the probabilities, that was a beta, and the authors here, van der Pas and van der Waart, computed the Bayesian posterior, okay, and maximize the posterior with respect to z. And they do all the computations, and the proof they presented worked also for the maximum likelihood, but they only obtained a rate bigger than log square of n over n. So they said they filled all the details that Bickel and Shen didn't do, but they obtain a suboptimal rate here. So this proof the consistency of the Bayesian estimator can be extended to the maximum likelihood estimator, but with a suboptimal rate. So, in our work, we defined a slightly different Bayesian estimator that we called integrated conditional likelihood, because instead of taking the posterior, we take an integrated version of the likelihood with a priori probability over the matrix P and not over pi, because the distribution of pi does not affect the results. And so this was better for our purposes. So we only took a priori distribution over the matrix P, and we do the integration of the likelihood with respect to this prior distribution, and this was called integrated likelihood. Okay, so we studied the maximum likelihood estimator and this version of the Bayesian estimator that is not exactly the same as van der Pas and van der Waart, but is related to it. So we obtain a weak consistency result with Andresa for these two estimators, the maximum likelihood and the integrated conditional likelihood, showing that if you have n rho n going to infinity, then both estimators are weakly consistent. So the requirement is that this alpha, the alpha defining the minimal size, the minimal proportion in each community, obviously needs to be smaller than the minimal p, because pi is the minimal probability of a node being in a community. So you need the minimal proportion of a community. So this alpha needs to be less than this minimum pi, and in this case you don't need any other assumption, and you obtain the weak consistency even not knowing the parameters. And this allows us to have an alpha decreasing with n, because if alpha decreases with a specific rate, a small rate that depends on n and rho n, then the estimators remain consistent, weakly consistent. And this, in turn, allows us to make k to grow with n, because as the condition is, you have this condition because the size of the community the minimal pi a needs to be smaller than 1 over k. So in this case, you have a condition on k, so if k grows with a smaller rate than this expression, that depends on rho n, then you will have weak consistent estimators for the communities. So we think that these results are not new from the are not new because are new in some sense in the general case, because the results, the proof results, are for the two communities model, and we do not know results allowing for k to grow with n. In principle, I don't know any result showing consistency when you allow k to grow with n. Okay, in general, the results are for fixed k.
Could you please show us again the integral with a priori?
Yeah. Of the definition here of here.
So new depends on n.
No, because P is a k by k matrix. So this is P is fixed and depends on P is a k by k matrix.
K is fixed.
K, in principle, yes. In the k is fixed. We do all the computations for k fixed, and then, but we obtain some rates depending on k. Okay, and then this allows you to extend the k to grow with n. So we have only an a priori for P that is a mixture or is a product of beta distributions, because each entry in the matrix is a single parameter, a single probability. So we use a beta 1.5 and a 1.
Using A and B.
Yeah, we are using all this.
So A and B, not A and B, not the same notation.
No, but this is another confusion of my notation. because in the papers people use A and B for the parameter, and in our we use A and B for the nodes, for the communities. Yeah, this is something that is.
I guess Pablo also using A and B. No, you are doing something else.
No, here you can say A and J, I and J, yeah. Here we can put I and J. It's not the same A and B, sorry. It's
No, because Antonio was asking if P depends on N. Is this a K?
P does not depend on N.
No, I think that maybe K was not known or could increase.
No, let me
So
see.
you're taking P equal this matrix with A and B multiplied by rho n.
Yeah, you are right. Let me see, because this is an a priori. Okay, now this is an a priori for a priori for P, okay? But this is an a priori, does not depend on N, because it's a prior distribution. Does not depend on N. But then when you compute what happens is that these counters, as you are assuming that the true P depends on N because it's decreasing with N, then this will grow slowly, will not grow as N square P. But I think there is no, okay, but this is an a priori for the matrix. P is fixed, that not depend on N, okay? And okay, so this is a new result, and for the strong consistency we obtain a condition, a constant that depends on the parameters, because here I have another notation, because in general, as I said, in the sparse model we are assuming that P is of order rho n, okay? So we reparameterize the model as P being as rho n times S, where S is a matrix with positive entries. and constant bounded entries. Okay, so we rewrite the model with a matrix S with fixed and bounded entries and this rho n outside. So this is the parameters of this matrix that are equivalent to this A and B here. Okay, you put the rho n here, you put the rho n here, and you have these coefficients. Okay, that are not the same A and B that here appear here. These are A, I, and J. Okay, are not the same A and B. All the A and B are different, right? And okay, so we have this constant that in the case of the model with two communities agrees with the usual constant of AB, that if you compute this for the model with two equal size community, you obtain the usual A minus B squared, okay? Where these are these A and B. These are these A and B, okay. Sorry, so the result on exact recovery is that if this constant is greater than 1, you obtain the exact recovery of the communities with probability going to 1 as n goes to infinity. And in the case of the Bayesian estimator, the integrated likelihood estimator, we have a suboptimal condition here depending on k. So, but this condition is the phase transition condition of Mossel and Abbe that they obtain for the two communities model, okay? And something that is also nice is that we obtain the consistency for at the constant, exactly at the constant. That was like an open problem in this case for in the this one for the maximum likelihood estimator, not for the Bayesian, because for the Bayesian you have a suboptimal condition. We do not know if it is consistent at the optimal constant. Okay, we don't know how to prove that it is optimal at the optimal condition. Okay, so this is basically the result we obtain for maximum likelihood and the modified version of the Bayesian estimator. Okay, a weak and strong consistency. And I'm briefly comment on a work we did before, because in the PhD, in the Andresa PhD, she worked on the identification of the number of communities, because we were interested in identifying the number of communities of the model and not the communities, because there are somehow extensive literature on the community detection problem. So we began to work on the identification of the number of communities. I'm going to pass this not so in detail. So for the identification of the number of communities, we proposed, but before this work, also a Bayesian estimator based on some a priori distributions for the pi, that was a Dirichlet, the prior distribution, and also a beta for the probabilities. And with this, so this is the prior distribution, the exact expression of the prior distribution, and you do also the integrated likelihood. That is this expression. You integrate the marginal distribution of your network with this prior distribution, and you obtain what is known as Krzyzewski-Trofimov estimator of the variables, of the random variable, that here is the adjacency matrix. So with this estimator, we defined an estimator for the number of communities. So the estimator of the number of communities was the logarithm of this distribution, of this Krzyzewski-Trofimov distribution, with a penalty that depends on k and on n, because when you want to estimate the dimension of a model, you need to do model selection. In general, you need to regularize your likelihood in order to obtain the exact dimension. Okay, so with this estimator, the penalty have an expression like this one is tricky, but it depends on the logarithm of the size of the network and on the k that was the communities, the number of communities. So in this work, we proved that this estimator was consistent for the number of communities. Okay, so this was a previous work where we used this Krzyzewski-Trofimov estimator because we learned how to prove the consistency about this estimator. But what okay, so this is the reference. It was published in 2020, and then these results were generalized to degree-corrected stochastic block models in another article by Cerqueira, Gallo, and Cristel, that was a former student of Sandro, and was written in a paper that is now submitted. So the generalization for the degree-corrected model, there is a model that have more parameters, and okay, I'm not going to enter in details here. But, and in this work, we show some simulations showing that, okay, the communities were competitive with the other estimators in the literature in general, and was also nice, or was better, here is the blue line here, the proportion of correct estimation is bigger here, for networks with unbalanced communities, because in general, many of the known estimators work well on balanced models, but when you go for models with unbalanced communities, they do not work. No, yeah, I know. Okay. Here? Okay. No, okay. This is a proportion. So no, this is sorry. This is the raw parameter. This is in function of the raw parameter, that is the sparsity of the network, and this is the proportion. I know it's very, very small, and this is the proportion of correct estimation of the number of communities. So our estimator, the KT, is the blue line here. So here is more or less as the other are better. Here, our estimator was compared with a penalized likelihood approach that was proposed by Bickel. That this was this one red, that was not very good. And in this column we have balanced networks. Okay, so all the communities have the same, basically the same size in this column. And in this column we have unbalanced networks. So here, for example, the proportions are 0.2, 0.5, and 0.3. So you have 30% of one community, 50% of another. And in this case of unbalanced network, the KT estimator is better than the other. Okay, it's only to show that this estimator for the number of communities was competitive with the method that was at that time. But I wanted to show this because to talk briefly about some work in progress, because before beginning to work on the community detection problem, we wanted to prove that the BIC is consistent for detect the number of communities. The BIC, the Bayesian Information Criterion, is a very well-known criterion for model selection in statistics, and in this case for estimating the number of communities. But it's an open problem to show that it is consistent in this case. So we want to prove that the BIC is consistent, and when we began to work on this problem, so the BIC is the maximum likelihood with a penalty of this order. So we are working, when we began to work on this problem, we realized that we had good results to do community detection. So we decided with Andresa to change and to write first the community detection. That was the results I showed before. Okay, but only to say that our Our goal is also to prove that the BIC is consistent. This is in progress, and there are some other works in progress. For example, there are some interesting open problems, like the relationship between the community detection problem and the unsupervised classification when you do clustering, and how to consistently choose the number of clusters, for example. So we are also working on this problem, and also how to find something that I didn't mention is how to compute efficiently the communities for very large network, because I show you the definition of the maximum likelihood estimators and of the Bayesian estimators, but I didn't mention that computationally they are not very good, because if you want to really compute these estimators, you need to search in the entire space of labels, of vectors of size n that is enormous, and you don't have, in general, efficient ways to do it. So we are studying this problem with Inés, Pablo, and Nicolas, and how to, and trying to find efficient algorithms for large networks. Okay, so I think it's all this. I have some references, and okay, thank you very much.
It's an obvious question. Yes. Do you think it's a smallest maximized criterion works here?
You say it's not so evident for me, because in the smallest maximizer criterion we obtain these nested models, and here you have an order on K.
We put everybody together and then you see this.
Okay, maybe.
Seems to be a universal property.
Yeah. But you have the order for K, the natural order, because here we have the natural order because they are integers. Okay, we don't have this representative that we had in the small. But I think so, yeah, because you can try to see all the behavior of all the models for different K and try to select on based on the box plots.
What do you say together? You estimate K and then you look for communities.
Okay, this is the next step. Okay, yeah, because we, as I said, we were only working on the estimation of K because there were methods to estimate the communities, to detect. So we thought, okay, if you can estimate K, then you can use any other method to detect the communities. But when we were studying the estimation of K, we realized that we could do, or we could prove the exact recovery of the maximum likelihood at the sharp constant. So we decided to write this. But I think that if we put together now, we need to work a little more on the model, on the consistency of the BIC. So we let this to a future work. I think it should work. Yeah.
Perhaps it's the same question, because you have this result where you estimate K and then you have some estimation based on knowing K. So is this the natural thing to do, or can you, or should you have a simultaneous estimation of both K and the other problem?
Yeah, so because you can treat K as another parameter. So in general, yeah, the best to do would be maybe to estimate all all together. But in general, I don't have here the expression for the BIC, but in general, when you estimate the number of communities, you have an expression like this KT that is here. Let me see here. So you have the argmax of some likelihood, okay, with a penalty. If you fix K, this is the same, in general, is the same function you use to estimate all the other parameters and to do community detection. So you have all in the same procedure in some sense, because here you only need to change K and choose the K that maximizes this, but when you maximize this, you have this that you use to detect the other thing. So in some sense, it's the same procedure. They are not separate procedures. And for the BIC is the case.
From the mathematical point of view, this is important. These values are important. What is kind of problem you have?
No, they are not specifically important. We use these specific distributions because they are the distributions you can conjugate with this multinomial. Yeah. You say the specific parameters? No, I think they are not relevant for in general. You can generalize this to other parameters.
You can also put up the same spirit that maybe a prior of K by using a process which is related to this Chinese restaurant. There is a model of people entering the restaurant, the number of tables that are filled by them.
Mm-hmm.
So the number of tables would be prior on the number of meals.
Mm-hmm. Yeah. What? Poisson? Yeah, I think there are some approaches doing this prior on K and integrating overall the things, but in general you don't have theoretical results about them. But I think there are people doing these priors. Yeah. Mm-hmm. Yeah, the penalty you can interpret it as a prior on K in some sense, because it's a prior on the number of communities. Yeah.
There are results for perhaps could you, for example, using the techniques that you use, for example, detect if the graph is heterogeneous against there is a certain community?
I don't know results about testing this type of hypothesis, but I cannot say if it would be possible. I think it would be nice to.
Yeah. Because one of the most important models in neurobiology is the model of cortical column by Potts and Disman, which is a stochastic block model. And I guess they decide to put the quantities, the number of communities, using uniquely neurophysiological criteria. But maybe from a point of view of statistics, this is not the right way. And I remember that you, long time ago, when you worked with the phylogeny globin, if I remember correctly, you found a dependency from the past that in some positions you could have different amino acids just by looking statistically. And then Hugo Melillo or someone said, well, but this was not. So maybe here, if you could apply a good statistical criterion to the data of a cortical column.
Okay, maybe you have here a specific
The
like.
question is not continuous scale.
I know. Yeah, you have the.
K, and you are testing K equal 1.
Yeah, k equals 0. Yeah.
No, I'm sorry, I think
You are testing K equal 1.
To t equal. Yeah.
K greater than 1.
Yeah.
But
It's-
You know how to estimate
But
K.
your system is not k equal 1, it's k equal 12 maybe.
No. Erdos range is K equal 1.
No, okay, but Poitiers-Diesma is a stochastic block model, and they decided for biological reasons to put, I guess, 12, I don't know, 12 or maybe something like this.
but-
And maybe you could find it directly by regularities.
Yeah, but I think Ricardo is right in the sense that the criterion is like a likelihood ratio, so you can do a likelihood ratio test with.
Just because somehow it's connected to what Patricia said, the test is easier. Maybe the conditions n times small n going to infinity, you can relax it. Still be able to detect if the graph is average mean against
Only to maybe I'm not sure. You cannot relax the hypothesis to have almost exact recovery because it's a necessary condition to have almost exact recovery of the conditions, but maybe for testing I'm not sure. Yeah.
Be specific. And
Here.
this stochastic block model that they is using fix A in diagonal, B
Outside? No, I think it's a simplification of the model because when you have two communities, you say, okay, we are going to assume that you have the same probability to connect nodes in the same community and a different probability, but there is no real. No, here you need the metric has to be symmetric because you do not consider the order of the nodes. Here is B, okay, but this does not need to be equal. You can have different probabilities to connect nodes in each. No, I think it's only a simplification for the computation, but not a real. And in our case, we assume any parameter, okay? We do not, first of all, we assume that they are not known. So you need to estimate the parameter from your data. Yeah. Yeah. You estimate it from the sample, but people that assume that parameters are known in general made some hypotheses to simplify the approach. Okay. Thank you.
The post-fixation right now.